Hello everyone, welcome to another video of Intro to Machine Learning. In this video, we are talking about resampling methods. So there are many resampling methods such as cross-validation and bootstrap. However, in this video, we are focusing on cross-validation and I will eventually zero in on KFold cross-validation. From the definition perspective, a resampling method refits a model of interest to obtain additional information about the model. And cross-validation is one such technique, is a model validation technique used for assessing results of a model when applied to test data. Okay, why is this important first of all? We'll revisit the bias variance trade-off in general. We saw that when we plot prediction error, and there is more detailed discussion of this in the previous video. So prediction error versus complexity of the model, complexity or flexibility as we called it in the previous video, which means a low complexity model, which is maybe a linear model, and then there is a high complexity model, which can be a higher degree polynomial, right? What really happens is that if we look at the the training data for each of these models, we saw that there is a continuous decline in the prediction error as we increase the complexity of the model for the training set. However, we are more interested in the test set because eventually that's what our model has been built for, right? And we saw a curve like this for the test set where the overfitted model or a higher complexity model sits somewhere here in the test data curve, and a low complexity model like the linear model sits somewhere here, and this eventually pointed to something of this structure, a low bias. This is the region of low bias and high variance, and the left hand side is the region of high bias and low variance. So obviously, whenever we are building our model, we have to deal with prediction error estimates, essentially this curve, right? And we have to come up with techniques to somewhat come up with a model that at least lies somewhere in this range, somewhere that lowers our test estimate. Because if you think about it, this test data would be nothing, but in real world applications, in real world scenario, this is going to be something that's unknown, right? So how do we deal with prediction error estimates? That's the question here. Now, a few methods have been listed here. So maybe I can get a large test set and then keep testing my model on a larger test set and then get a better maybe estimate of the error and maybe get a better choice of a model, right? But practically speaking, this is almost next to impossible because we already do not have access to larger data sets. And in this situation, we're talking of having a large test set. So this is somewhat difficult. We can make mathematical adjustments, for example, the error rate that's used to estimate the test error. And some of the methods are AIC, BIC, CP statistics. I'll talk about each one of those in some of the lectures that are coming up. But in this lecture, we're talking about another class of methods in which we hold out, or maybe you can say separate out, some part of the training set observations from the fitting process. So when I'm building the model, I'll hold out a subset, right? And then create the model from the rest of the data that's not held out, right? And then test on this held out observation. Okay, what does that mean? That's so the basic technique for that is known as the validation set approach, right? This is the basic, and then from this method, we'll go on to the KFold cross-validation. Okay, so this validation set approach essentially asks us to divide the available sample, whatever my training set is, into a training and a validation set, right? Fit the model on this training set, right? And then calculate the error using this validation set. This is going to be my error estimate for the actual test set on which my model will be applied. Again, we assume whenever we are building a model that test set is essentially unknown, right? We don't know. And so we're making an error estimate using the validation set. Let me actually make you visualize this. So let's say this is my entire training data, right? And in the validation set approach, what I do is I divide it into two parts. So this is my training data now. half, right? Half of this, and the other is the validation. And the validation actually acts as a test set, essentially, because that's all we have, right? We have the training set only, right? And so this acts as a validation set, and then we train our model on only this, right? And then test our model on the validation set. That's the basic idea. Now, there are some drawbacks of this validation process. For example, as you can see, this seems wasteful because, as we said earlier, we already have limited data, right? And then I separated half of it for training. So my model was essentially built on just, let's say if there were n observations, just on n over 2, and the rest n over 2 was not used, right? So it is a little bit wasteful, not utilized. The other issue that might arise is high variability in validation estimate of the test error, obviously because we have this huge set that we've kept only for testing, right? So there could be a high variability in there. And then validation estimate, the estimate of the error using this part of the data, can sometimes overestimate the test error for the model fit on the entire data set. That's because, just think about it, more the data, lower the error. And we already divided this data into half, right? So all those are some drawbacks of the validation process. And in order to overcome those drawbacks, we come up with something that's known as KFold cross-validation, right? So this is another approach for estimating the test error. The idea stays similar to the validation test approach, with the exception that we're not dividing the data into two parts. Rather, we are dividing it into k equally sized parts. K could be any number, right? So that's what K stands for in KFold cross-validation. What we'll do is we'll leave out or hold out that part K and fit the model to the rest of the K minus 1 parts, obtain the error predictions for the kth part, the held out part, and then keep repeating this process and calculate the average of all these stages. So these are also known as stages in KFold cross-validation. Let me actually show you how this looks like. So for example, this is my entire data, right? So validation set will be just one of them. So I'm just calling it val. And then the rest of the parts, and let's say I divided it into k parts. K is a number, right? So then the part 1, part 2, part 3, and so on up to somewhere here k minus 1th part, right? So I'm going to train my model on only these, right, and test it on this. And then maybe my validation will be this in the next stage, and this will become part 1, and then I'll train my model again and calculate the average eventually, right? So in terms of the math, I'm calculating something that's known as a score, right? So this is denoted by CV, and for any kth part, let's say I decided that this is my validation and the rest of them are my training. So this validation is my test part, right? And then again, I'm going to hold out a part and then test for the rest. And so my overall estimate for the error is going to be the sum of all these errors that I have for each part, right? So k from 1 up to, let's say there are k parts, total k parts in the entire data set. And I calculate the weighted average, and n is the number of observations of the mean squared error calculated for any of these k parts, right? So k is essentially taking values 1, 2, 3, as you saw here, and so on. So this is the score that essentially we calculate, and this is going to be the estimate of the error or of the test error, right? And as you can see, we are utilizing the same data set again and again, but some part of it to test the error and then calculating the average of that error. This, in most cases, this is a better estimate of the test error as compared to just having one part as the validation and the other as the training, right? And then, so this was about how KFold cross-validation works. There are obviously some issues with cross-validation, essentially related to the value of K, right? So the value of K has to be chosen with like real experimentation, and good understanding of the data itself. Picking K is important because it can introduce a bias in the score or the CV that we just saw, right? Or it can introduce a high variance, right? So a score with a high variance can may change a lot based on the data used to fit the model, or a high bias, right? So even the score has that tendency to have a high bias or a high variance. So if K is small, right? If K has a very small value, we just split it into, let's say, 2 or 3 parts. We splitted the data into very few parts, right? So if K is small, then the score might get biased. Just remember this. And if K is large, sometimes you can get high variability, right? So again, it is subjective. It is dependent on the type of data that you're using. And so there are ways to find out what is the best value of K. Mostly K should lie between 5 to 10 for most of the cases. It gives a good error estimate when K is chosen between that range. Okay, so that was about KFold cross-validation. Let's look at a simple example in Python to better understand that. So let's keep this and go to Spider. So I'm looking at one of the examples that we looked earlier in the course. So this was about estimating the housing prices. So I have the square feet living, and using that square feet area, I'm trying to predict the price of a house, right? So the rest of the stuff stays the same. I'm importing libraries and data and then creating a train test split. All of this has been dealt with earlier. So all of this I'm not going to repeat. Let me just execute it and fit a linear model. Notice I'm fitting a linear model and then predicting the predicting the results on the test set, right? So this is like the original. I shouldn't have printed all of that, but that's okay. Right, so I have some predicted values on the test set based on the model that I created, and that model is my linear model. Okay, now let me utilize this predicted value and then see the mean absolute error. I've also provided this code in the description below, so you can also check for the mean squared error. I'm doing it for the mean absolute error because we can actually relate to the actual values when you're looking at mean absolute error versus the squared prices, which is going to be a huge number, right? And if you're interested in looking at the mean squared error, you can just uncomment this part and then go from there. Okay, so I'm looking at the mean absolute error just because the values are more relatable. So this is 141,000 is the mean absolute error for the model, the linear model, right? You can check the error for polynomial models. For example, a quadratic model, we've looked at it before. So I'm looking at degree equals 2, right? And using the polynomial features from the scikit-learn pre-processing. And again, there is a cubic model as well, right? So checking the results for these two models, because here the complexity is increasing. Let's see what happens to the, okay, I haven't, let me import this. And notice the error value, right? So the error value earlier was 141,625, right? Then it came, so with the polynomial degree 2, it went a little above and then started to come down. Obviously, we are overfitting here, and I'm checking it with the test set that I created earlier, right? So that's that. But what we are really interested in is the KFold cross-validation, right? So here is the code for that. I'll walk you through the entire thing. Let me just focus only on this part. And so just remove everything else. Yeah. So the first step in KFold cross-validation is to import the KFold class, right? So let me do that. And I'm creating an instance of this, and notice the n splits. So how many parts do you want to split it into, right? How many folds do you want? Like we had the example where I said k could be any number, so that k here is 4, right? So I'm beginning with 4. You can definitely experiment with other numbers. Let me create that instance. Okay, so there's that. I'm creating an empty list called scores, and then essentially I'm putting all different scores for each fold mean absolute error, and then calculating the mean of those scores. So that's all I'm doing here. And notice here in scores, I'm doing an append to the list, and I'm appending the mean absolute error. So essentially, this is how the mean absolute error can be used. And this is again imported from the scikit. Let me see, I imported it somewhere. Yeah, here. So if you are worried what is this mean absolute error, all you have to do is from scikit-learn.metrics import mean absolute error. Similar to that, you can do as the look at the commented part, you can do a mean squared error as well. So it's up to you. Just because this is more relatable, I did a mean absolute error. You could definitely do a mean squared error and calculate the overall mean. Okay, so here notice the average or the mean, and this is, by the way, the score that we looked at here. The CV that I said is calculated and we were looking at mean squared error. Obviously, I'm looking at mean absolute error here, right? So the actual error for each fold, right? And then I calculated the mean. It really came down if you look at it, like it's 135 something. And if we remember, and let me actually print this again, the mean absolute error for the linear model was around, okay, so did I do something wrong here? We already had the value. Let's go back and see what that was. Okay, I have to run the entire thing. So just remember 135 and the original error that we got was 141, right? So it did come down and it's giving us some estimate of the actual error that we might encounter when using a linear model. Um, and when we are using KFold cross-validation, it's giving us a better estimate of the test error, right? Now, so this was like just demonstrating how to choose different values of k. For example, let's say if we choose a value of k equals 5, and then let's see what happens here. We get a different value of the error, which is closer to the one that was initially that we got initially when we were just using a train test split, right? So you should go ahead and play sort of with this and see how well the error estimates are when you actually go and play with different values of n splits, right? Okay, so one really useful thing here is like the whole discussion started for model selection, right? So how to select a better model and using this KFold cross-validation. So one easy way of doing that is like this is something that I did, and you might like just try to look at it once. So what I'm doing is I'm importing something called cross-val score. This actually gives me the score directly using some input parameters, for example, model, and then the actual train, the actual data. So this X current is nothing but I'm creating different polynomial fits starting from the linear model. So that's what I'm doing. I'm creating different models and then using a split of size 4, right? I'm trying to find out whose mean absolute error is the smallest, right? Notice here there is a parameter called scoring. I'm using any g underscore mean absolute error. You could use a mean squared error, and it's going to give you the output in the form of a mean squared error. And then the CV is going to take the number of folds, essentially. You can directly give it a number as well. That's the good part about cross-val score. However, I'm taking cross-validation from the KFold itself. Okay, so let's see how this works. And definitely go ahead and play with the n splits. As I said earlier, instead of 4, use different values. So here, so this is what my loop does. I started with the degree 1 polynomial, which is a linear model, and then went ahead with 2, 3, 4, 5, 6, and so on. It's giving me the mean absolute error for a split on the actual training data of size 4. I can increase or decrease this n splits and see which model gives me the lowest mean absolute error, and then maybe choose that model and go from there, right? So this was just a demonstration of how to utilize KFold cross-validation. There's no right and wrong answer to which model to select. It totally depends on the data you're working with. It depends on the problem you're working with. We look at KFold cross-validation again with a classification problem once we're done with support vector machines. Okay, thank you.